By the time you go to sleep tonight, the biological machine sitting inside your chest will have contracted 100,000 times. It will push nearly 2,000 gallons of fluid through a closed network of vessels stretching 60,000 miles. This sustained performance is possible because the heart functions as a heavy-duty mechanical pump, engineered for constant high-pressure output. This pump must solve a constant physics problem. It receives a flood of used, oxygen-depleted blood returning from the organs, while simultaneously handling a rush of fresh, oxygen-rich blood coming from the lungs. It has to process both streams at high speed without ever letting a single drop mix. The heart achieves this separation through a highly specific architectural layout, utilizing 4 distinct isolated chambers. Mapping the engineering of these 4 rooms reveals the spatial logic that makes human life physically possible. If we slice the pump open, we find that the interior is divided into 4 distinct rooms, functioning as 2 synchronized sub-pumps working side by side. The vertical layout separates the workload. The 2 top rooms, the atria, act as low-pressure receivers. Their only job is to passively collect the blood as it pours back into the heart. Immediately below them are the ventricles. These are the heavy lifters of the system. They are built with thick, muscular walls, designed to forcefully eject the blood out into the body under immense pressure. Horizontally, the system is permanently divided by a thick wall of tissue called the septum. This barrier creates a complete physical seal between the right and left sides, ensuring the 2 different streams of blood remain isolated. This barrier allows the heart to operate a continuous dual-loop circuit. The right side takes in the dark, oxygen-poor blood returning from the body and pumps it straight to the lungs to gather fresh oxygen. That newly oxygenated, bright red blood flows back into the left side of the heart. From there, the massive left ventricle fires it out with enough force to reach every single cell in the body. This 4-chamber, dual-sided architecture forms a figure-8 circuit, allowing the human body to oxygenate its blood and distribute it simultaneously. Moving fluid through 4 interconnected rooms at high pressure introduces a mechanical risk, backward flow during a contraction. To prevent this, the heart relies on 4 one-way mechanical valves. These act as biological doors between the chambers. The exact millisecond the blood passes through, the valves snap shut, creating a watertight seal. The lub-dub sound of a heartbeat is the acoustic reverberation of these mechanical doors slamming shut under pressure. For these doors to function, the muscular walls need a signal telling them the exact microsecond to squeeze. That signal comes from a built-in power source. Tucked into the upper right chamber is a cluster of cells called the sinoatrial node, serving as the body's natural electrical pacemaker. This node generates an electrical spark that travels down microscopic biological wires woven through the heart muscle. The charge systematically shocks the chambers, commanding them to contract in a precise top-down sequence. This system functions through the integration of an independent electrical grid, timing a set of mechanical doors to move fluid through 4 optimized rooms. There is one critical architectural flaw in this design. The pump distributes oxygen-rich fuel to the entire body, but the heavy lifting muscle of the heart itself must also be fed. The thick muscle walls cannot absorb oxygen from the blood passing through their internal chambers. Instead, they are fed from the outside by a web of tiny, vulnerable pipes called the coronary arteries. Because these pipes are so narrow, they are susceptible to blockages. A diet heavily reliant on trans fats and simple sugars causes sticky plaque to accumulate along their interior walls, gradually narrowing the passage. If a clot breaks loose and forms a blockage in one of these narrowed arteries, the blood flow stops, oxygen is cut off, and the specific section of the chamber wall fed by that pipe starves and begins to die. This 4-chamber engine is capable of beating independently if given oxygen, yet its survival is entirely at the mercy of its external plumbing. We maintain this system by consuming healthy fats to keep the pipes clean, managing stress to keep the electrical grid firing calmly, and utilizing cardiovascular exercise to physically thicken the chamber walls. The 4-chamber architecture provides the blueprint for survival, but maintaining the integrity of the plumbing is a deliberate mechanical responsibility.